we did it, yes. So, welcome everybody to the seminar of today. Sorry for being a bit late. We have with us today Giorgio Saracco, he's a postdoc here in Sissa, and he will talk about minimizer of the prescribed curvature functional.
So, hello everybody, and thanks Manuel and Maria for asking me to deliver this seminar. What I want to talk today about is the shape of minimizer of a given functional, which is the prescribed curvature functional, and the outline of the talk is more or less this one. So first thing, I will introduce you the functional, give you some a priori properties of minimizers, and I show how there is a link with the Cheeger problem, which is something that Nicolau talked about the past week. Then we switch to the Cheeger problem, and I'll give you a geometric characterization of the shape of minimizers and a way to approximate the constant. Done that, we switch back to the prescribed curvature functional, and I'll give you a geometric characterization of maximal and minimal minimizer, and I will make clear what a maximal and what a minimal minimizer is. And at last, I will give you as an application, which is to the isoperimetric problem. So without further ado, let me start. And this is the function we'll be considering. So take any Borel set in Rn and fix at a constant k. We will associate to this set E the following energy, which is given by the perimeter of E minus k times the volume of E. Now, by volume of E, or mass, I denote the usual n-dimensional Lebesgue measure, while by perimeter, I mean the variational perimeter, which is also known as Cacciopoli or the Giorgio perimeter. Now, if you don't know what this variational perimeter is, it is enough to know that if your set is regular enough, say Lipschitz, then the perimeter coincides with the n-1 dimensional Hausdorff measure of the topological boundary. And the other thing that is important to know is that this perimeter functional is lower semi-continuous, and this is basically all we need to know for this to properly follow this talk. So what we will be doing today is fix an open bounded set in Rn and a positive constant k, and we seek to minimize this functional fk among the subsets of omega. So we look for the infimum of perimeter of E minus k times volume of E among the subsets of omega. Now, the first thing, there are some a priori properties. Suppose you have a non-trivial minimizer. By non-trivial, I mean that its mass is positive. Then you can find out a few things. Now, first thing, this is just a dilation argument, and you can prove that the boundary of the minimizer k intersects the boundary of the box omega. Now, the other property I will tell you about now directly comes from the following observation. Suppose Ek is a minimizer, then actually K is minimizing as well the perimeter functional among all subsets of omega with its same volume. So in some sense is a perimeter minimizer with a volume constraint. And these kind of sets have been widely studied starting from the 50s with the Giorgio and so on. And we have a bunch of regularity properties that were proved that we can deploy immediately. And we find out that actually the boundary of Ek meets the boundary of omega in a tangential way whenever the contact point is regular. This means that if there exists an outward normal at x, and x is the contact point, then there exists the outward normal at x also for the boundary of Ek, and the two normals actually coincide. Moreover, the internal boundary of Ek, so the boundary of Ek inside omega, inside the box, is actually analytic up to some, say, negligible set. Say up to dimension 7, you are analytic. And actually, this internal boundary has constant mean curvature equal to the prescribed k times some dimensional constant. And this is more or less the reason why this functional is called prescribed mean curvature functional, because the minimizers have mean curvature given by the k you fix at the very beginning. Now, this property is much stronger in 2D, because in 2D, you have that the internal boundary is like n-1 hypersurface. So in 2D is like a curve, union of curves. And actually there are only two kinds of curves with constant curvature that are arcs of circle, or say union offs, and segments, which if you want are somehow the limit as the curvature goes to 0. So in 2D, what you actually get to know from these properties is that the internal boundary is a union of arcs of circle whose radius is the inverse of the prescribed curvature k. And this is basically the reason why we will be talking today of the planar case, so when the box omega is in R2. And clearly in higher dimension, you can't have like a similar characterization, because just thinking surfaces in 3D, well, you have surfaces with constant mean curvature, for instance, spherical cups, cylinders, revolution surfaces generated by catenoids, onduloids, and so on. So this property is really gives you much more information only in 2D. Now, that said, these are some a priori properties. Do we actually know there are minimizers, say even non-trivial minimizers? Now, existence of a minimizer is always granted, and this is because, as I told you at the very beginning, the perimeter functional is lower semi-continuous. Now, it may happen that you're unlucky, and there is a unique minimizer which is given by the empty set, or say a set with a 0 mass. Now, since the empty set has 0 energy, you can easily say the following. Now, if the perimeter of E minus k times the mass of E is strictly positive for all subsets with positive mass, well, then you have no choice. The empty set has to be the unique minimizer. Now, conversely, if there is at least one set F such that it has strictly negative energy, then you have the existence of non-trivial minimizers. Then from these two, say, inequality, you can actually see that there is a threshold value of k, of kappa, which is the guy who decides if whether or not there exist non-trivial minimizers. And this value is the Cheeger constant of the set omega, which is defined as the infimum among all subsets of omega with positive mass of the ratio perimeter over volume. And this, as I told you, acts as a threshold to existence of non-trivial minimizers. Indeed, you can restate the first case when the empty set is unique minimizer in terms of the constant h, as if the prescribed constant kappa is strictly less than the Cheeger constant, then you have a unique minimizer which is given by the empty set. On the converse, you can restate the second case as if the prescribed constant k kappa is strictly greater than the Cheeger constant h, then there exist non-trivial minimizers. Well, and then there is the limit case, k equal to h, which somehow the two cases glue together, and you have at the same time the empty set and non-trivial set, which minimize the functional. And the non-trivial sets are called Cheeger sets, and are those sets C which attain the Cheeger constant. So are those sets C such that the Cheeger constant of omega is equal to the perimeter of C divided by the volume of C. So these set C's are, so finding this set C and computing the constant H you usually refer to as the Cheeger problem. Now, I hope I made clear that it's important for studying this functional f, fk, to actually know the value of the Cheeger constant H, because it's the guy who tells us if the problem is interesting or not. And this Cheeger constant actually comes up in many different situations, such as this one, existence of sets with prescribed mean curvature. It comes up in spectral inequalities like the Cheeger and Boozer inequality, which Niccolo talked about. it comes up in landslide modeling, it comes up in reimage reconstruction, and many other different contexts. So it's somehow it's scattered all around the literature. So first thing I want to do now is to switch to this Cheeger problem and try to figure out if there is some way to compute the constant, because it's what we're really interested in, because it's the constant is the threshold value which we're interested in, and give you a characterization of the shape of minimizers for a class of sets. So are actually minimizer, so Cheeger sets, easy to characterize, and is there some smart way to compute the constant? So let me give you a few examples. First one is take the box omega to be a ball. And now this set here has a unique Cheeger set, which is given by the ball itself. And this is basically a consequence of the isoperimetric inequality. And from now on, in all my figures, unless noted, the grayed out area is the minimizer. So let's pass to some more exotic box, say like a square. And okay, since the square is symmetric, well, we expect the Cheeger set to be as well symmetric, to enjoy the same symmetries. And since its boundary must be made of arcs of circle with the same radius, well, you can more or less imagine that the shape has to be like the one I depicted. So you can actually write down a minimization problem in one variable, the radius, because you can actually compute perimeter and volume of sets that are made like this, and you just need to minimize. And so this is very easy. Now, from these two examples, you might wonder that is there always a unique Cheeger set? Because in these two cases, it is unique. Well, no. And for instance, I give you this example, a balanced dumbbell. Take two balls of same radius, say one, spaced far apart one from the other, and link them with a thin tube. Well, if the tube is thin enough, then you have actually three minimizers, which are given by the left-hand side component, the right-hand side component, and the union of the two. And this is because actually the class of minimizers for the prescribed curvature functional, so in turn for, say, the Cheeger problem, is closed under countable unions and countable intersections. Okay, now for the Cheeger problem, whenever you intersect, you need to require that the intersection is actually positive volume. So in this case, you end up, when you intersect, you end up with the empty set, which is not a Cheeger set. Nevertheless, it's still a minimizer of the prescribed curvature functional with the choice k equal to the Cheeger constant. Okay, and again, now you can see that this is the minimizer, but just by writing down some computation, because you can imagine that this is the shape that it must have. But so far, I didn't really provide you like any meaningful input in how to compute the thing, unless, okay, looking at the shape and somehow imagine who the and try to guess who the minimizer is. Is there something more general for some class of sets? Well, when I started studying the problem back in 2014, there were basically two classes for which we had a recipe to compute the constant and determine the minimizer. And these were convex sets and strips. So a strip is basically the diffeomorphic image of a rectangle. Say you take a curve, say C2, with some bound on the curvature, and you enlarge the curve by T, where T is bounded from above the curvature. And this prevents the sets you're creating to self-intersect. Okay, so basically it's the diffeomorphic image of a rectangle. Now in these two cases, if we denote by omega t, omega superscript t, the inner parallel set at distance t, which is the closed set of points in X whose distance from the boundary is greater than or equal to t, so it's a subset of omega, closed subset, then whenever omega, the box is convex to a strip, you have uniqueness of the minimizer, so a unique Cheeger set, which is given by the Minkowski sum of the inner parallel set at distance r summed with the ball of same radius, okay? By Minkowski sum, if you don't know what it is, you can imagine the following thing. Just take a ball of radius r inside your set omega, and you start moving it around as much as you can. The set you end up covering, or coloring, say, is exactly the Minkowski sum. Okay, so this is what we're doing. Place a ball of radius r, move it around. The thing you end up coloring is your minimizer. Now, this r is not just a random value, it's actually the inverse of the constant, okay? So once you know the constant, you immediately know who the minimizer is by this procedure. Now, moreover, this characterization tells you there is also a formula to compute the constant, because it tells you that this r is the unique positive solution of this equation, pi times t squared equal to the mass of the inner parallel set at distance t. So in this case, whenever your box is a convex or a strip, you can solve this equation. By solving it, you find essentially the constant, because the solution is the inverse of the constant. And then the characterization tells you what the minimizer is. You take a ball of that radius, the inverse of the constant, inside omega, move it around as much as you can. Well, the area you color is the unique minimizer. So this is a very elegant theorem and very nice. But there is something that should be bugging you. If you were to draw a Venn diagram of convex set and strips, well, the two things overlap, but they're not one containing into the other. So it's a completely natural question to wonder, is there actually a bigger class which encompasses both convex set and strips for which this characterization holds? Well, it turns out there is, and this is exactly what we proved with Gianpaolo Leonardi and Robin Neumayer. So the first thing is you need to realize what is the common feature that convex set and strips have. And this, if you have to guess, is absolutely unclear what is the key point. But if you were to read through the proof, you would realize that what is really important is to be able to move any ball of a given radius on any other ball of the same radius containing in the set. So let me give you this definition. We say that the set omega has known x of a given radius r if whenever you take two balls of that radius r containing omega, you can drag in a continuous manner one onto the other without ever exiting the set. Now this means there exists a continuous curve gamma whose start point is the center of the first ball, whose end point is the center of the second ball, and whenever you center a ball of radius r on this curve, then that ball is containing in omega. Okay, so if you want to imagine the thing, you can take the first ball, move it onto the second without exiting the set. And well, this condition is actually necessary if you want to that characterization, that geometric characterization to hold. Otherwise, it can fail, and it can fail in both directions. So I give you two examples. Okay, you must require it with the r given by the inverse of the Cheeger constant. And I give you two counter examples if you don't require it. Now, for first thing, this say unbalanced dumbbell, take a ball of radius 1 and a ball of radius 2/3, spaced far apart, and join them with a thin tube. Now, in this case, there is a unique Cheeger set, which is given by a perturbation of the ball of radius 1. So the Cheeger constant is going to be very close to 2. So if you were to follow the recipe, you would be using balls of radius very close to 1/2 and move those around. But in doing so, you would cover not just the Cheeger set, which is given by essentially the ball of radius 1, but as well the ball of radius 2/3. So in this case, the union of all the balls with the prescribed radius strictly contains the minimizer. It can happen as well the opposite. So take, for instance, this bow tie or butterfly domain. So essentially you take a rectangle and you select the midpoints of the long sides and you start pinching them one toward the other. Now, if you pinch enough, but not too much, you can prove that there is a unique Cheeger set, which is the one depicted in figure, but the union of the balls of the correct radius are somehow blocked from the neck, and they don't flow through the neck. So the union of all the balls of correct radius this time is strictly contained in the minimizer. So it somehow seems that you really need this condition for the inverse of the constant. Otherwise, the characterization may fail in both directions. There is one more example I would like to give you, which is the following. Now, you might imagine, and this is completely reasonable guess, as I told you that the internal boundary is made of arcs of circle of radius r, the inverse of the constant. Okay, just consider the disk which draws one of these arcs, okay? So it's completely reasonable to think that, okay, if you consider the whole disk, well, then the disk is going to be contained in your Cheeger set, or at least in, say, in your box omega. Well, this is in general false. For instance, this R domain, if you consider the disk that draws the internal boundary, well, the disk is not contained in omega, okay? So there is also this behavior. So basically what we can prove is that by requiring this necessary condition of non-x of radius the inverse of the constant is not just necessary, but it is as well sufficient. And indeed, this is what we proved. So take a planar set omega, bounded, and require this no bottleneck condition for radius r, the inverse of the constant. And then we require some topological assumptions on omega. And we require that omega is a Jordan domain, which means that its boundary is a Jordan curve. And we require this additional condition that the volume of the boundary of omega, so the volume of the curve, the two-dimensional Lebesgue measure of the curve, is 0. This essentially rules out like very bad behaved curves like plane filling curves, say a la piano, okay? Piano curves are not Jordan curves, but there are similar Jordan curves which fills the plane. Those are called Osgood-Knob curves. Now, under these two sets of assumptions, you basically have the same theorem as you had for convex sets and strips. Indeed, you can prove that the maximal Cheeger set is given by the union of all the balls of correct radius. And again, you have the inner Cheeger formula. So the constant is the inverse of the unique positive solution of this equation. Now, one thing I would like to remark is that before I told you that for convex set and strips, I told you, well, the unique Cheeger set is given by this guy. Now, when you pass to this more general situation, well, uniqueness is no more ensured, but the formula, this geometric characterization, holds for the maximal Cheeger set. And by maximal, I mean the following. Recall that I told you that the class of minimizers is closed under countable unions. So there is a way to define a maximal Cheeger set, say as the union of all minimizers. You can make it formal. And well, our theorem proves that this maximal minimizer is given as this geometric characterization. Now, what about uniqueness? We can still prove uniqueness under one additional assumption, which is the following. If the inner parallel set at distance r, so the points in omega whose distance from the boundary is at least r, if it coincides with the closure of its interior, then you have uniqueness, okay? So this is basically the extension of what we had for convex set and strips, but you can't really employ it in the same manner. Before, you could solve the equation and then use the recipe to find the minimizer. Now, you can't really solve the equation because as a hypothesis, you need a priori to know the value of the Cheeger constant, okay? Now, you can actually weaken this hypothesis, making it independent from H in the following way, if you want. You require the set omega, the box, to have non-x radius in a certain range in which, for some reason, you know that the inverse of the Cheeger constant must fall within. You can always provide upper and lower bounds to the constant, one, for instance, with the isoperimetric inequality, and the other bound by using any competitor inside omega, say omega itself, or say the biggest ball you can fit in omega. And once you have a range of values where h must fall within, well, you get a range of values for of radii. And if your set is non-x in that range for radii in that range, well, then you can actually solve the equation and then use the recipe to figure out who your maximal minimizer is. Okay. Now, some more remarks on the topological assumption. Well, there is this request that the volume of the boundary is 0. Now, this is unclear if it is necessary. I believe it is not, but it allows us to prove that minimizers are open, which is nice. And on the other hand, the request that omega is a Jordan domain is somehow needed because it ensures that your box omega is simple connected, and this is a key piece to the proof. And if you drop this assumption, you can have counterexamples. Say, take for instance a ball of radius 1 and drill a hole very close to the boundary of radius epsilon. Well, if the epsilon is small enough, you can prove that the whole set is a Cheeger in itself. But really, the union of all the balls of the correct radius will never completely fill the set. Okay. What about uniqueness? Now, why can uniqueness fail? As I told you, we have uniqueness when this set equality holds. So when the inner parallel set at distance r coincides with the closure of the interior. Let me give you an example when uniqueness fails. And this is what we call the Pinocchio shape. Take a ball of radius 1 and consider a half line exiting from the center. And along this half line, let's slide a ball of radius r very close to 1/2, and this r, you can actually compute what this r needs to be. And for this precise value of r, by keep sliding this ball further and further away, you get this kind of shapes, which resembles a face with a drawing nose. So that's where the Pinocchio name comes from. And you can prove that all these shapes have the same Cheeger constant and they're all Cheeger in themselves. So you end up having infinitely many Cheeger sets. So if you stop this ball sliding at some point, you have a set and which has infinitely many Cheeger sets. And why is this actually happening? Okay, this guy is non-x of radius of any radius. Okay, so you can use our theorem and you would actually find that the maximal minimizer is the whole set itself. But as I told you, it has many more other minimizers. And well, why is this happening? Well, because in the inner parallel set at distance r, there is a submanifold of dimension 1. There is this curve, which is in the case is a segment. And that's the reason why uniqueness fails. And by doing this operation of taking the closure of the interior, you're somehow canceling out these one-dimensional submanifolds in omega r. So if omega r coincides with the closure of the interior, this behavior cannot occur. So you can rule out the existence of multiple minimizers. Okay, what else? Well, as I told you, you have the formula to compute the constant, which is very nice. But at times, and I will give you an example in the next slide, you can't really write down the equation, or even if you can, maybe you can't algebraically solve it. So it is useful to have some way to approximate the constant. And what we can prove is an error estimate of the constant with respect to interior approximations. So suppose you have two open sets, one containing into the other, so small omega containing big omega. And suppose that the inner Cheeger formula holds for both, and call a small r, every time I say small is something related to like the small omega, and big R is related to big omega. Well, what you can prove is that the difference of the inverse of the Cheeger constant. So the inverse of the Cheeger constant corresponding to big omega minus the inverse of the Cheeger constant corresponding to small omega. Well, it's bounded from below from 0, but what is interesting is that we can bound it from above with the following quantity, which is given by the mass of the set difference of the inner parallel set at distance small r of big omega minus the inner parallel set at distance small r of small omega divided by 2 pi times r, okay? So you have this error estimate. You approximate big omega from within the interior with small omega, and then you can approximate the constant of the shear constant of big omega with the one of small omega, and you can control the error. And this formula tells you how much you're away from the correct value. Now, and as an example, we can consider the Koch snowflake, which is built in an iterative way. You start from an equilateral triangle, say of side 1, and at each step you replace the middle third with an outward equilateral triangle. And you go on, and at the limit you end up with what is known as the Koch snowflake. Now, if you try to write down the formula for this guy, well, it's a nightmare. Maybe if you're smart enough and you write it down in base 3, you can manage it. I don't know, we didn't have success in doing so. But the good thing is that the approximating sets of the snowflake here are from the interior, and they're actually polygonal, and you can write, I'm not saying that it's easy, but you can write and actually solve the inner Cheeger formula for these polygonal approximations. And if you use the previous proposition, you can prove that the difference between the inverse of the constant of the snowflake and the inverse of the constant of the nth iterate is bound from above by this number, 2 to the n minus 3 divided something, which goes to 0 quite fast. And indeed, I think that R8 approximates the constant up to the 10th decimal digit. Okay, this was more or less what I wanted to tell you about the Cheeger problem. Now we switch back to the prescribed mean curvature problem. Now we somehow know how to compute the constant for a class of sets, which is good, because then for that class of sets, okay, maybe we know for which values of k we have non-trivial minimizers. And we would like to treat the problem and describe the shape of minimizers for general k greater than or equal to the constant. Now, what turns out is that the geometric characterization I gave you for k equal to the Cheeger constant h or omega, well, actually is a shared future for minimizers of fk. In the sense, well, you just need to replace instances of h with k, with general k. So you have this theorem, which says that take a planar domain omega, take fix kappa constant greater than or equal to the Cheeger constant. Okay, assume the same topological assumptions as before on the domain omega. Assume that omega is non-x of radius now the inverse of the prescribed curvature k, kappa. Well, then again, the maximal minimizer is given by the union of all the balls with suitable radius r, okay, where r is still is now the inverse of the prescribed curvature kappa. And again, you have the same characterization for uniqueness. Now, proving this theorem gives us a few interesting corollaries, say. First one is that we can actually improve the case when kappa is equal to h. We can now prove, okay, yes, this is the same theorem. What we can actually prove this corollary, which says that we can now actually, we can solve the inner Cheeger formula and consider the unique positive solution, and then check if the set is non-x for that value. Well, if it doesn't, then that value is the inverse of the Cheeger constant, and then you have the recipe. If you recall, before we had to ensure that the set had known x in some range where you knew that the inverse of the constant fall within. Now we can actually solve the formula at the very beginning, check if we have known x, and then if we don't, well, then that R is the inverse of the constant, okay? And you also get the characterization of the minimizers. Okay, one other thing is a criterion, a sufficient criterion, which tells you if a set is a Cheeger set in itself. So this means that that the Cheeger constant of omega is equal to the perimeter omega divided by the volume of omega. And this is the criterion. Take a set omega, planar set, with the same topological assumptions we made throughout the talk, and suppose that the complement set has reached at least volume of omega divided by the perimeter of omega. Well, then omega is a Cheeger set in itself, which means that the Cheeger constant of omega is equal to the perimeter of omega divided by the volume of omega. Now, if you don't know what the reach is, you can think of the following. A set A has reached at least R. If you can roll on the boundary on the from the exterior a ball of radius R. So in this case, this hypothesis that the complement has reached at least this number means that you can roll a ball of radius this number inside omega along the boundary. This is what we're more basically saying. And okay, this criterion essentially becomes as well necessary when the set is convex, when the box is convex. And with it, you can prove that you can find a way to build, say, self-Cheeger sets. If you take a closed set whose mass is given by pi times r squared, and this set has reached strictly greater than r, well, then the Minkowski sum of this small omega with the ball of radius r is self-Cheeger. Okay, now I would like to turn our interest to, say, minimal minimizers. So far, we characterized the maximal minimizers. And since I told you that we have uniqueness when the omega r is equal to the closure of its interior, it's completely reasonable guess to think that, okay, maybe my minimal minimizer, so say the intersection of all minimizers, because I told you the intersection of the countable intersection is of minimizer still a minimizer. So you can define a minimal minimizer in a suitable manner, and more or less you end up proving that is the intersection of all minimizers. So since you have uniqueness when omega coincides with the closure of the interior, well, it's reasonable to think that your minimal minimizer is given by the closure of the interior, Minkowski sum with the ball of radius r, okay, with the same r, which is the inverse of the constant you prescribed. Now, let us consider this example where the dark gray set is the inner parallel set at distance r. So your candidate to be minimizer is the light gray set. And in this case, well, okay, two balls save radius 1, and the thin tube has width exactly r, being r the inverse of the curvature you prescribed at the very beginning, okay? Now, if we suppose this guy is a minimizer, then we can consider one ball of radius r, the one that was defining the internal boundary, and push it a bit forward inside the tube. And this you can do because we chose exactly the width of the tube to be twice r. Now, if you do so and push the ball along the curve by some length L, well, you're not really changing the energy because you are basically adding this yellow rectangle. So in perimeter, you're adding twice the length, so 2L. And in volume, you're adding, well, twice the width, so 2 times R, times the length. So you're adding twice R times L. Well, and since R is the inverse of the curvature, you end up seeing that the difference in perimeter minus K times the difference in volume is 0. So you didn't change the energy with this operation. So if the guy at the very beginning was a minimizer, this one is again a minimizer. So you just keep pushing forward this ball and you keep creating minimizers. But at some point you end up with this situation, which should be a minimizer by from your initial assumption. But well, this guy has a singularity inside, okay? Is the boundary, the internal boundary is not analytic. So it can't really be a minimizer. So there is something amiss in our initial guess. Our initial guess cannot really be the minimal minimizer. And well, what we proved is that essentially this is the only thing that can go wrong. And indeed, what we did was to characterize the set difference in a parallel set at distance R, set difference with the closure of its interior. And we showed that if you take a Jordan domain with non-X of size R, then this set difference is basically made of two families, possibly empty, of regular curves. And these curves essentially correspond to the two things we saw, either Pinocchio's noses or this last example, so let's say always corridors. So indeed, you can prove you have the curves belonging to the first family are those whose such that one of its endpoints belong to the closure of the interior and the other not. And the curves in the second family have both endpoints in the closure of the interior. And then you actually prove that the set difference is given exactly by the image of these curves. And then if you want, you can prove that the first family, so you can have a finite number of, say, noses. And well, you can have countably many hallways, but the sum of the lengths of the curves corresponding to those hallways is finite. Well, once you have this, say, structure, well, you can prove who the minimal minimizer is same set of assumptions. Well, the minimal minimizer is the Minkowski sum of the ball of radius R with the closure of the interior omega union the images of the curves in the second family. So the curves which corresponds to all to hallways. And well, then you have uniqueness as soon as you have no Pinocchio's noses. So we basically have a shape description for the maximal and the minimal minimizer for any set which has non-X or radius, the inverse of the curvature you're prescribing. Now, what we can get as a corollary are the following. Now, if your set has non-X of a given radius, then you can always find a minimizer of any volume within the range from the volume of the minimal minimizer and the volume of the maximal minimizer. And the standard way to interpolate is just grow noses from the minimal minimizer to the maximal one. In doing so, you basically fill the whole gap, and doing in this procedure is, say, continuous in the volume. Then you have some nestedness properties. Suppose that your set is non-X for two different radii, say R2, say, okay, so K corresponding to curvatures K2 and K1, with K2 bigger than K1. Then you have some set inclusions, namely the maximal minimizer corresponding to the greatest curvature, well, clearly contains the minimal minimizer corresponding to the same curvature, but this guy in turn contains the maximal minimizer corresponding to the smallest curvature of the two, which in turn contains the minimal one. And then we also have some sort of uniqueness result. Suppose that your set is non-X of all radii, okay? Then you have at most countably many curvatures K for which your prescribed curvature functional is not a unique minimizer. And what we do is basically apply these properties to the isoperimetric problem. So this, I want to give you this as an application. The isoperimetric problem is what follows. You fix omega, and you consider the functional j, which to each volume v, so v is something, is a value between 0 and the mass of omega, associates the least perimeter needed inside omega to enclose the given volume. So you look at the infimum of the perimeter E among all subsets of omega whose volume is V, is the given V. Now, as I told at the very beginning of the talk, if you have a minimizer of the prescribed curvature functional, well, then that minimizer is as well a minimizer of the isoperimetric profile for the volume choice V equal to its own volume. So it's somehow, so how can I say, you can hope to build isoperimetric sets through the unconstrained problem of the prescribed mean curvature problem. And this is basically what we did with Gianpaolo. We proved that if your set omega is a Jordan domain with whose boundary is 0 volume, and if omega is non-x of all radius rho, for rho in between 0 and the inverse of the Cheeger constant, well, what you can do is basically apply the geometric characterization I gave you before, and you knew as well that there was a standard way, say, to interpolate between the volume of the minima and the volume of the maximal. So you can actually prove that for all volumes greater than or equal to the volume of the minimal Cheeger set, well, you can find a curvature K greater than or equal to the Cheeger constant and a minimizer of the prescribed curvature functional with prescribed curvature K, such that, well, it has volume exactly V, and such that this EK is actually an isoperimetric set. Okay, and if you want, you can actually choose the family of minimizer to be increasing with respect to the set inclusion. So this somehow is a way to build all minimizers, all isoperimetric sets for the above some volume threshold for this special class of sets that are those omegas with non-x of any radius. Okay, what's nice of this characterization is that same set of assumptions, if you define this map G, which is defined from the Cheeger constant of H to infinity, so maps basically takes a curvature value in between H and plus infinity and maps it in the minus the infimum of the prescribed curvature functional in omega with the choice of curvature kappa. Well, this map is convex, so its Legendre transform is well defined on the range of volumes, volume of the minimal Cheeger set up to the volume of omega. And what is really interesting is that this Legendre transform coincides with the isoperimetric profile on such an interval. And well, since the Legendre transform maps convex functions in convex functions, well, you can prove that for this class of sets, well, the isoperimetric profile is convex in that range of volumes. So the very last thing is the following, which is something which is ongoing with Gianpaolo. And okay, take the same set of assumptions. And now suppose that you have non-x for all radius, not just up to the inverse of the Cheeger constant, but up to the inverse of, so this is not the inverse, but up to R, where R is the inner radius of omega. So the radius of the biggest ball you can fit in your set. Okay, what you know is, well, that the isoperimetric profile is convex above a certain threshold. well, below a certain threshold, which is given by the volume of the biggest ball you can fit in, well, the isoperimetric profile goes like the square root of the volume, and its square is convex. Now, what we are doing with Gianpaolo is we prove that actually the isoperimetric profile is convex above the volume of the greatest ball you can fit in omega, and actually its square is globally convex. So this is a forthcoming result, which is probably coming out, I don't know, maybe before Christmas, something like that, as Christmas gift. Okay, just one caveat, because this is a question I receive quite often. If you have ever dealt with isoperimetric problems, you might have heard that the square of the isoperimetric profile is concave. And I'm claiming that it is convex. Now, what's amiss? Well, there are two different isoperimetric profiles, the relative one and the total one. Now, the isoperimetric profile whose square is convex is the relative one. So it's the map that to each volume associates the least perimeter, say, associates the infimum of the perimeter E inside omega among all subsets of omega whose volume is V. So in this first case, for minimizers, sticking to the boundary of omega is free. They don't pay anything, okay? And so you look at the relative perimeter inside omega, and the square of this guy is concave, and this is a well-known result. What we're looking at is the total isoperimetric profile, so we look to minimize the total perimeter of E inside omega, and the square of this guy is convex. So in this second case, which is the one we consider, sticking to the boundary of omega is no more free. You pay something in the function for doing so. And well, this is all I wanted to say, and I thank you for the attention.
Thank you, Giorgio, for the very nice seminar. Now it's moment for questions. So if you want, you can unmute yourself and ask questions. Okay, Giorgio, maybe ask you one question about Cheeger set in the Pinocchio case, because I'm a bit confused. In that case, we don't have uniqueness, right?
No, you don't.
Which are the examples of Cheeger set?
Minimizers.
We can describe the Cheeger set in that case. It's similar to the dumbbell.
Okay, so this is the case. Basically, take a ball of radius 1, okay? Mm-hmm. And take another ball and let it slide along this half line, okay? And you create this kind of set. Now, there is a precise value of the radius of this ball you let slide, which is such that the set you end up building is Cheeger in itself. Okay, so say, consider this first dashed line, okay? Mm-hmm. Not the one of the ball, but the first one, okay? The first one inside.
Yes, yes.
So, okay, this guy is a Cheeger set in itself, and is a Cheeger set in the whole set.
And then if you translate it on the right,
and if you translate it, you're not changing the energy. The computation is exactly the same as the one before, as the one for the dumbbell, because you essentially add something in perimeter, which is twice the length of how much you're moving, and you add in volume twice the radius times the length, but the radius was chosen exactly to be the inverse of the constant in this case.
Okay.
And this radius is not going to be 1/2, it's going to be very close to 1/2. I think it's something like 0.56, something like that. There are computations somewhere telling you exactly which radius you need to pick.
Okay, thank you.
You're welcome.
Yeah. To be honest, it's not very clear to me also the example of the snowflake there, but actually the theorem before. I didn't understand very well the theorem that you use in the example. So the example is built because you want.
The snowflake is built by taking, first thing you take like, can you see the arrow on my screen?
Yeah.
Yeah, okay. So the first iteration is this, like, say, triangle equilateral triangle, okay? The second iterate is this, say, star, okay? And so on. So for instance, this guy here, the one depicted below is the, I think, the first iterate, okay? So since the snowflake has non-x of any radius, so in particular, it has non-x for the inverse of its Cheeger constant, you can apply our theorem. So you know it, the inner Cheeger formula holds for this guy, but the same holds for his approximating sets, okay? Mm-hmm. So what we do is to compute, so the previous theorem tells us that we can approximate the constant of the snowflake with the constant of this guy, okay? And in doing so, we do some error, which is controlled from above by this quantity. Okay, so it's controlled from above by the inner parallel set of the snowflake at distance small rn. So this is the inverse of the constant of this guy. Set difference with the inner parallel set at distance small r of this guy, okay? And well, you can actually do the computation and estimate this guy from above, and in doing so, you get this like estimate error.
Okay.
So the trick ends up being able to compute the constant for the approximating sets and being able to, say, estimate the volume of this set difference, the mass of this set.
So this fractal example, you can estimate the Cheeger, right? The Cheeger constant of the limit set via the Cheeger constant of the approximation. That is easier.
Exactly.
Okay.
But this in general is true. You can always, since the Cheeger constant is monotonic decreasing with respect to set inclusions, you can always do this sort of estimate. But you don't know. But in general, you don't have like any control of on the error you do. In this case, because of our proposition, you know what's the error you're doing.
Okay, thank you.
I hope I made it clear.
No, this. Okay, it seems to me that there are no questions. So there are no more questions. We thank Giorgio again, and we can meet next Friday for the next seminar. Thank you all. Bye.
Bye. Have a nice day and weekend.
Allora.